A narrow, faint spectral feature appeared in observations of 3I/Atlas, the third confirmed interstellar visitor to pass through our solar system. It showed up near wavelengths astronomers associate with water or its chemical byproducts. Weak enough to doubt, persistent enough to worry. The signature wasn't bold. It hovered near the noise floor, the statistical boundary where real signals and random fluctuations become difficult to separate. But it appeared more than once. Different observing nights, separated by days, recorded something in approximately the same place in the spectrum. That repetition matters. A single spurious line, an instrumental glitch, a cosmic ray hit, a misidentified telluric feature from Earth's atmosphere, can vanish under better processing or fail to reproduce when the observation is repeated. A real line, tied to the object itself, should track with the object's motion, should Doppler shift as the relative velocity between Earth and the target changes, and should survive careful calibration and background subtraction. The feature detected around 3I/Atlas did some of these things. Not all of them cleanly. Not with the confidence that turns a candidate into a confirmation, but enough that teams began comparing notes quietly, running additional reductions, checking whether independent datasets showed the same hint. The timing made it stranger. The signal arrived during a period when 3I/Atlas was changing brightness and viewing geometry, when the object was faint, when photon counts were low, and when calibration errors and false positives are statistically most likely. Those are exactly the conditions under which astronomers are trained to be skeptical. Water is a loaded word in planetary science. It carries implications about composition, about activity, about the potential for chemistry, and the history of an object's formation environment. So the threshold for claiming a water detection is high, especially for an interstellar visitor where the stakes of misinterpretation are compounded by the rarity of the target and the brevity of the observational window. The mystery is not water exists. Water is common in the universe, abundant in comets, ubiquitous in the cold outer regions of protoplanetary disks. The mystery is why this clue appears now, in this form, with this level of ambiguity, and whether it reflects real molecular emission from 3I/Atlas or a confluence of noise, atmospheric contamination, and the limits of what faint spectroscopy can resolve. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentary. Water in space is slippery to detect. Astronomers rarely see HEO molecules directly in the way a chemist might identify water in a laboratory sample. Instead, they infer its presence through radiative fingerprints, specific wavelengths where water molecules absorb or emit light as they rotate, vibrate, or dissociate under ultraviolet radiation from the sun. But those wavelengths overlap, sometimes precisely, with absorption features in Earth's own atmosphere. Water vapor in the air above a telescope absorbs infrared and certain visible wavelengths so strongly that ground-based observations in those bands become impossible without extraordinary corrections. Observers at high-altitude sites, mountain tops where the air is thin and dry, gain some advantage, but even there, telluric contamination remains a constant adversary. The atmosphere doesn't just dim the signal uniformly, it imprints its own spectral structure, creating absorption lines that can be mistaken for features, originating from the astronomical target, if the correction isn't handled carefully. So astronomers often chase water's trail through proxies. Hydroxyl radicals, the dissociation product of water molecules broken apart by sunlight, emit at specific ultraviolet and radio wavelengths that can be observed from the ground or space. Oxygen emission lines, particularly the forbidden transitions seen in tenuous cometary comae, can indicate the presence of water vapor being photodissociated into its constituent atoms. Hydrogen emissions, part of the Lyman alpha line in the ultraviolet, trace the hydrogen atoms liberated when water molecules are destroyed by solar radiation. Thermal signatures, broad features in the infrared, consistent with the sublimation of water ice, can also serve as indirect evidence, though they require ruling out other volatiles like carbon dioxide or carbon monoxide that sublimate at similar temperatures. The logic chain is careful. What would count as a strong proxy? A detection of O emission at the expected brightness for a given gas production rate, combined with imaging that shows a coma consistent with dust lifted by sublimating ice. What would count as weak? A tentative line at low signal-to-noise, seen in one dataset, without corroborating evidence from other wavelengths or other nights. And what types of artifacts can mimic the same spectral shapes? Imperfect flat fielding that leaves residual gradients in the detector response. Misidentified night sky emission lines, particularly from atmospheric oxygen or sodium, that sit close to the target's expected position in the spectrum. Contamination from field stars partially overlapping the object's trace during extraction. Each of these can produce narrow features that look, at first glance, like molecular emission. The investigation becomes a forensic checklist, run before the word water enters a draft paper. Is the feature aligned with known telluric absorption or emission bands? If so, was the telluric model subtracted accurately, or could residual atmospheric signal remain? Does the feature track the object's Doppler shift? Does it move in wavelength as the object's radial velocity relative to Earth changes from night to night? Or does it stay fixed, like a terrestrial artifact anchored to Earth's reference frame? Does it appear in multiple nights, multiple instruments, multiple reduction pipelines applied to the same raw data? Or does it emerge only in one lucky dataset, sensitive to specific choices about background subtraction or wavelength calibration? These questions are not rhetorical. They are tests, and the answers determine whether the signal escalates from possible glitch to candidate detection or collapses back into noise. For 3I/Atlas, the feature survived some of these tests, but not all. After subtracting atmospheric models, using high-resolution telluric templates derived from nearby standard stars observed on the same nights, the line weakened, but it didn't disappear. That's significant. If the feature were purely telluric, proper correction should erase it. The fact that a residual remains suggests either that the telluric correction was imperfect, which is plausible given the faintness of the target and the difficulty of extracting a clean spectrum from a moving object in a crowded field, or that parted field of the signal originates from the object itself. The Doppler test provided a second piece of evidence. The feature's wavelength position was consistent within measurement uncertainty, with a line that would shift as the object's velocity changed. Not perfectly consistent, there were small discrepancies, offsets of a few tenths of an angstrom that could be attributed to wavelength calibration errors, or the imperfect centering of the object's spectrum on the detector slit, but close enough that dismissing it as a fixed artifact became harder. And when independent reductions were run, different teams using different extraction algorithms, different sky subtraction techniques, different ways of combining multiple exposures, the feature reappeared, sometimes stronger, sometimes weaker, but present in enough cases that the null hypothesis, there is no line, started to feel uncomfortable. Yet skepticism had another card to play, the coma that isn't there. If water ice is sublimating from the nucleus of 3I/Atlas, producing enough gas to generate a detectable spectral signature, you expect visual companions. Dust liftoff, because sublimating ice drags dust grains from the surface into space. Coma brightening, as that dust scatters sunlight and makes the object appear more diffuse and extended than a bare nucleus would. Characteristic color changes, particularly a reddening or bluing depending on the size distribution of the dust grains. And perhaps measurable non-gravitational acceleration, the rocket effect that occurs when outgassing is asymmetric and produces a net thrust on the nucleus. But the imaging data for 3I/Atlas looked restrained. Too clean. Too quiet. The object appeared faint and compact in most images, with at most a very faint, symmetric haze that could be attributed to seeing conditions and the imperfect subtraction of the point spread function. No dramatic tail. No jets. No obvious signs of vigorous activity. The brightness curve showed some variability, but it was subtle, and it didn't correlate cleanly with the epochs when the spectral feature was detected. That contradiction creates tension. If the spectrum whispers chemistry, gas emission, molecular activity, something happening that requires energy and material escaping the nucleus, why does the eye see so little? Several scenarios can reconcile this. A low dust-to-gas ratio means that even if gas is being released, the amount of dust entrained in that gas is small. producing a coma too faint to stand out against the sky background or to significantly alter the photometry. Activity can find small vents. Localized regions on the nucleus where volatiles are exposed and sublimating would produce gas emission without the global brightening or extended coma that widespread surface activity creates. Rapid photodissociation, where water molecules are broken apart by solar ultraviolet radiation within seconds to minutes of being released, would generate O and other dissociation products detectable in the spectrum while limiting how far the parent molecules travel before being destroyed. That process can create a compact emission region close to the nucleus, too small to resolve spatially, but bright enough in certain wavelengths to produce a spectral signature. Each of these mechanisms keeps the gas emission real while maintaining a visually subtle appearance. But each also makes specific predictions about the spatial distribution of emission, about the brightness in different spectral bands, about how the signal should evolve with heliocentric distance, and testing those predictions requires data that the current observations, constrained by the object's faintness and the limited time available before it fades further, do not yet provide. Physics offers another test, the heat budget. If the spectral clue is real, does it make sense energetically? Astronomers can estimate a rough gas production rate from the strength of the observed feature, the distance to the object, and assumptions about the excitation conditions and the fraction of molecules in the emitting state. That production rate, converted into a sublimation flux, can be compared to a simple thermal model. How much sunlight is hitting the surface at 3I/Atlas's heliocentric distance? How efficiently that energy is absorbed and conducted into HO, the subsurface, and how much ice must sublimate to carry away the deposited heat. If the implied activity is too high, requiring more solar energy than the object receives, or more surface area than the estimated nucleus size allows, the water clue becomes suspicious, possibly an overestimate due to misidentified lines or incorrect assumptions about the emission mechanism. If the implied activity is too low, below the threshold where any reasonable thermal model would trigger sublimation, that also raises questions. But if the numbers hover in a plausible range, neither trivially small nor impossibly large, the detection gains credibility, even if it remains tentative. For 3I/Atlas, the thermal budget sits in the uncomfortable zone. Possible, but not tidy. The estimated gas production rate, if the feature is real and correctly attributed to water, or O, falls within the lower end of what comets at similar heliocentric distances typically produce. It's not unprecedented, but it's also not strong enough to leave unambiguous signatures in imaging or in the orbit. That ambiguity can be interpreted in two ways. Either the detection is marginal and should be treated with caution until additional data confirm it, or the object is genuinely undergoing weak, localized activity that doesn't produce the dramatic observational signatures of a more active comet. Delayed response becomes relevant here. Water ice, buried beneath a thin crust of dust and refractory material, can remain insulated from solar heating for hours or days, sublimating only when heat diffuses deep enough to reach the ice layer. That delay can cause activity to lag behind the object's orbital position, turning on after perihelion or when certain surface regions rotate into sunlight and remain illuminated long enough to heat through. Jets that activate only at specific orientations, when a vent rotates into direct sunlight, or when the thermal wave reaches a particular depth, can produce intermittent emission, visible spectroscopically during brief windows, but absent or undetectable at other times. The investigation tightens around this. The numbers don't fully break either way. They don't confirm the detection with high confidence, but they also don't rule it out. The spectral feature remains a candidate, and the thermal model suggests that weak water-driven activity is physically plausible given the object's distance, size, and the uncertainties in its surface properties. But plausible is not proof. It's a boundary condition, a constraint that keeps the hypothesis alive without elevating it to a verified fact. And if the clue is real, what does it mean? Water is not unique to any one origin. It's abundant in the solar system, present in comets from the Oort cloud and the Kuiper belt, detected in asteroids, found as ice on moons, and in the polar regions of planets. But the context matters. For an interstellar object, water's presence or absence, and the way it behaves under solar heating can hint at the formation environment from which the visitor originated. Compositional ratios become diagnostic. The relative abundances of water, carbon monoxide, carbon dioxide, methane, and other volatiles reflect the temperature and chemical conditions in the protoplanetary disk where the object formed. If 3I/Atlas shows water emission but little or no a volatile that sublimates at lower temperatures and is typically abundant in comets, that imbalance could suggest a formation region warmer than the outer edges of most protoplanetary disks, or a history of thermal processing that depleted the more volatile species. Conversely, if water appears alongside strong Co or Cu signatures, it would indicate a colder, more volatile rich composition. Isotopic constraints, if obtainable, would be even more powerful. The deuterium to hydrogen ratio in water, for instance, varies depending on the temperature at which the water ice formed, with colder environments producing higher DH ratios. But measuring isotopes in a faint, distant, interstellar object is extraordinarily difficult, requiring high-resolution spectroscopy and integration times that may not be feasible before the object fades. Even if isotopic measurements are attempted, the uncertainties will be large, and the results will likely be upper or lower limits rather than precise values. Every inference is boxed in by error bars and selection effects. Faint objects force short observing windows, low signal-to-noise data, and incomplete wavelength coverage. The net result is not a definitive origin story, but a map of what the water clue could mean. If it's real, if the spectral feature truly reflects emission from water or its dissociation products, if the thermal and dynamical context support the thermal and dynamical context, support the interpretation, that map includes possibilities. A volatile rich interstellar comet consistent with formation in a cold outer disk, a volatile depleted body that has been thermally processed, or even an object whose surface has been altered by cosmic ray exposure during millions of years in interstellar space. Sealing volatiles beneath a radiation-damaged crust that only now, under solar heating, is beginning to crack and release its contents. But the map also includes limitations. The water clue, as it stands, cannot justify claims about habitability, about the potential for life, or about anything beyond the basic chemistry of a small icy body responding to sunlight. Water is a simple molecule and a starting point, not an endpoint. And for 3I/Atlas, that simplicity is both the promise and the frustration. The detection, if confirmed, would tell us something about the object's composition and activity, adding one data point to the sparse catalog of interstellar visitor properties. But it would also leave vast questions unanswered about internal structure, about the history of the object before it entered the solar system, about how representative it is of the population of small bodies drifting through the galaxy. Looking forward, the opportunity to deepen this investigation is fading. 3I/Atlas continues outbound, receding from the Sun and Earth, dimming as distance increases. Spectroscopic observations become progressively harder as the photon flux drops, and the exposure times required to achieve useful signal-to-noise ratios grow prohibitively long. Within weeks to months, the object will be too faint for ground-based spectroscopy with current facilities. Space-based platforms like the James Webb Space Telescope, with its infrared sensitivity and ability to observe without atmospheric interference, could detect water signatures more cleanly if the object remains bright enough, and if observing time can be allocated. But GWST's schedule is heavily oversubscribed, and faint, fast-moving targets are logistically challenging. The VRSC Rubian Observatory, once operational, will revolutionize the detection of interstellar visitors, catching them earlier and providing dense photometric monitoring that can identify candidates for follow-up spectroscopy while they are still bright. Future missions, dedicated spectrographs on large ground-based telescopes, and improved atmospheric correction techniques will all contribute to better characterization of the next interstellar object. But for 3I/Atlas, the dataset we have, the tentative spectral feature, The ambiguous thermal context, the quiet imaging, may be the final word, at least until the next visitor arrives and the lessons learned here can be applied with better preparation. What remains is not a triumphant confirmation, but a better understanding of how difficult and how valuable these measurements are. Water is a simple molecule, yes, but detecting it, interpreting it, and extracting meaning from a faint, contested clue require discipline, skepticism, and the patience to live with ambiguity. Astronomy often advances not through dramatic discoveries, but through persistent anomalies that survive careful scrutiny, through signals that refuse to be dismissed as noise, even when they refuse to be confirmed as certainty. 3I/Atlas is what it has always been, an object that forces measurement to compete with interpretation, that sits at the edge of what current instruments and current methods can resolve, and that teaches us as much about our limitations as about the universe we are trying to understand. The water clue, faint and contested, is part of that lesson. It reminds us that we are learning how to listen better, how to measure cleaner, and how to stay honest when the universe speaks softly. The unanswered question is not failure. It's the space where science continues, where the next observation, the next technique, and the next interstellar visitor will return to test whether what we thought we heard was real, or whether it was only ever the echo of our instruments straining at the limits of perception.